Some conversations change everything, even when only two people hear them. I spent my final years at Princeton walking the same paths as Robert Oppenheimer, sharing the same corridors, the same troubled silences. People remember him as the father of the atomic bomb. They remember Einstein as the gentle genius with wild hair. But they never heard what we discussed in those quiet afternoons when the weight of what we had unleashed pressed down on us both. Einstein worried about more than politics or weapons. He worried about time itself, about whether our meddling with the atom had torn something deeper in the fabric of existence. These weren't the musings of old men losing their minds. These were the calculated fears of physicists who understood that energy and matter and time are not separate things, but one seamless whole we had learned to break apart. Before we continue, take a moment to notice where you're listening from, and if this story stays with you, you're welcome to return tomorrow for what comes next. I arrived at Princeton in the autumn of 1954, when the leaves were turning and the world felt like it was holding its breath. The Institute for Advanced Study had offered me a position in theoretical physics, and I thought I understood what I was walking into. A quiet academic sanctuary where brilliant minds could pursue pure research without the pressures of the outside world. I was wrong about the quiet part. The first thing I noticed was the tension. It hung in the corridors like smoke from a fire you couldn't quite locate. Graduate students spoke in whispers. Senior fellows avoided certain topics entirely. And at the center of it all was Robert Oppenheimer, the Institute's director, carrying himself with the careful dignity of a man who had learned to live under constant scrutiny. Just months earlier, the Atomic Energy Commission had stripped him of his security clearance. The hearings had been brutal, public, and thorough. They questioned his loyalty, his past associations, his judgment. They painted him as a security risk, a man whose communist sympathies in his youth made him unfit to advise on nuclear policy. What they really couldn't forgive was his opposition to the hydrogen bomb, his growing conviction that we were building weapons too terrible to use. But here's what the newspapers didn't capture. The hearings had freed him in ways his accusers never intended. When you can no longer influence policy, when you're no longer bound by security oaths and classified briefings, you can finally speak the truth. Not publicly, not dramatically, but in the careful conversations between colleagues who understand the weight of what we had all helped to create. My office was on the second floor of Fold Hall, 3 doors down from Einstein's study. I learned his routine quickly. He arrived each morning at 9:30, walking slowly, always alone. He'd nod to anyone he passed, but rarely stopped for conversation. His real discussions happened in the afternoons, usually over tea, often with Oppenheimer. Einstein was 75 that autumn, and the wild hair had grown wilder, the eyes more penetrating, but his mind remained sharp as surgical steel. I'd attended his lectures in Berlin 20 years earlier, before the war changed everything. Back then, he spoke with the confidence of a man who had unlocked the secrets of the universe. Now, I sensed something different, a wariness, as if those same secrets had turned on their discoverer. The first time I saw them together was in November. I was working late, struggling with some equations that refused to behave, when I heard voices from Einstein's office. The door was slightly ajar, and though I couldn't make out the words, I recognized the cadences. Einstein's careful English, touched with German precision. Oppenheimer's more fluid American speech, cultured and precise. I didn't intend to eavesdrop, but something in their tone made me pause. This wasn't the casual academic discussion you'd expect between colleagues. There was urgency there, and something deeper. Regret, perhaps, or fear. When Oppenheimer emerged 20 minutes later, his face carried an expression I would come to know well over the following months. The look of a man wrestling with knowledge too dangerous to ignore and too terrible to share freely. He nodded to me as he passed, and I noticed his hands were trembling slightly. That winter, I began to understand the true cost of what we had accomplished. The atomic bomb had ended the war, yes. It had saved lives by making invasion of Japan unnecessary, certainly. But it had also crossed a threshold that could never be uncrossed. We had given humanity the power to destroy itself, and we had done it with equations and theories that were beautiful in their elegance. Einstein's role in this haunted him more than most people realized. His letter to Roosevelt in 1939, urging American research into atomic weapons, had been motivated by fear that Germany might develop them first. He had not worked on the Manhattan Project directly, but his theories had made it possible. E equals mc squared wasn't just an abstract relationship between energy and matter. It was the key that unlocked the atom's heart. The hydrogen bomb was worse. Where the atomic bomb released the binding energy of heavy nuclei, the hydrogen bomb mimicked the sun itself, forcing light nuclei to fuse and release energies that dwarfed anything we had achieved before. Einstein had opposed it publicly, calling it a danger to humanity's survival. Oppenheimer had opposed it behind closed doors, arguing that no conceivable military target required such destructive force.
Both men had lost those arguments. The first hydrogen bomb test in 1952 had vaporized an entire island in the Pacific. The fireball was 3 miles across.
The mushroom cloud rose 25 miles into the stratosphere. And that was just the beginning. The Soviets tested their own hydrogen bomb in 1953. The arms race had entered a new phase, one measured not in thousands of tons of TNT equivalent, but in millions. By the time I arrived at Princeton, both Einstein and Oppenheimer had been marginalized by the very institutions they had helped to create.
Einstein's pacifist statements were dismissed as the naive idealism of an aging genius. Oppenheimer's security clearance revocation had silenced his voice in policy discussions.
But it had not silenced their conversations with each other. I began to join them for tea in December, at Einstein's invitation. The ritual was simple. Plain black tea served in delicate porcelain cups, the same set Einstein had used for decades. No elaborate ceremony, no formal agenda. Just 3 physicists discussing the implications of our work while winter light faded outside the tall windows. In those early conversations, I mostly listened. Einstein and Oppenheimer had a shared vocabulary of experience I was only beginning to understand. They spoke of Szilard and Fermi, of Los Alamos and Chicago Pile, one of the moment when theory became reality in the desert of New Mexico. They spoke of the weight of knowledge and the responsibility that comes with understanding forces that can reshape the world. But even then, I sensed they were approaching something deeper, some conclusion they were reluctant to voice, even to each other. Einstein would pause mid-sentence sometimes, as if hearing something the rest of us couldn't detect. Oppenheimer would study his hands, elegant fingers that had once calculated the critical mass needed to sustain a chain reaction.
The security clearance revocation letter sat framed on Oppenheimer's desk, not as a badge of shame, but as a reminder of what they had cost him for speaking truth to power.
It had stripped away his influence, but it had also stripped away his illusions. He was free now to think thoughts too dangerous for a government advisor to contemplate.
And Einstein, who had never needed security clearance because his opposition to weapons work was well known, was free to follow those thoughts wherever they led.
Einstein's daily routine never varied, and I came to find comfort in its predictability during those uncertain months. He arrived each morning at precisely 9:30, walking the tree-lined path from Mercer Street with the measured pace of a man who had learned to conserve his energy for what mattered most. His wild white hair caught the morning light, making him instantly recognizable even from a distance, but his expression remained distant, focused inward on problems the rest of us could barely comprehend. His study reflected the evolution of his thinking.
Where once the blackboards had been covered with the elegant mathematics of general relativity, now they displayed increasingly complex attempts to unify all the forces of nature into a single, coherent framework. The unified field theory consumed his days, this quest to show that electromagnetism, gravity, and the nuclear forces were merely different manifestations of one underlying reality. Most of my colleagues dismissed this work as the obsession of an aging genius who had lost touch with modern physics. Quantum mechanics had proven its worth through decades of experimental confirmation. The Copenhagen interpretation, with its embrace of fundamental randomness and observer effects, had become orthodox doctrine. But Einstein remained unconvinced, famously declaring that God does not play dice with the universe.
I began to understand that his rejection of quantum mechanics ran deeper than mere philosophical preference.
During our afternoon tea sessions, he would trace equations in the air with his finger, explaining why the standard interpretation troubled him so profoundly.
The theory yields much, but it hardly brings us closer to the secret of the old one. He told me one gray January afternoon, using his favorite metaphor for the divine order he believed governed reality. I am at all events convinced that he does not throw dice.
But it wasn't just about dice or determinism. Einstein had come to believe that quantum mechanics' probabilistic nature was a symptom of our incomplete understanding, not a fundamental feature of reality itself.
The unified field equations he worked on obsessively were his attempt to restore order, to find the deeper pattern that would make sense of what appeared to be chaos. His notebooks from this period reveal the scope of his ambition and the weight of his concerns.
Page after page of tensor calculations, geometrical proofs, attempts to express the electromagnetic field as a manifestation of curved space-time. But interspersed among the mathematics were more troubling observations.
Notes about the hydrogen bomb tests, calculations of energy release rates, questions about what such massive disturbances might do to the fabric of space-time itself.
Robert, he said to Oppenheimer during one of our tea sessions, when we speak of nuclear weapons, we think in terms of cities destroyed, of casualties counted in hundreds of thousands. But what if the damage goes deeper? What if we are tearing holes in reality itself?
Oppenheimer set down his cup carefully, the porcelain clicking against the saucer with unusual precision. What do you mean, Albert? Einstein moved to the blackboard, where his latest field equations covered nearly every inch of available space. General relativity tells us that matter and energy warp the geometry of space-time.
A massive star curves space around itself. When that star collapses, the curvature becomes so extreme that not even light can escape. We call these black holes, but we have never observed one directly. He paused, studying his own equations as if seeing them for the first time. But what happens when we release energies comparable to stellar processes here on Earth? What happens when we detonate weapons that convert matter to energy with perfect efficiency, creating temperatures that exceed the core of the sun? The question hung in the air between us. I had never considered the possibility that nuclear weapons might affect space-time itself, but Einstein's concern was grounded in rigorous mathematics. If general relativity was correct, and it had passed every experimental test so far, then massive energy releases would indeed create disturbances in the geometry of space and time. The first atomic bombs released energies equivalent to 20,000 tons of TNT, Einstein continued. Enormous by human standards, but trivial compared to natural processes. The hydrogen bomb changes this calculation entirely. The Castle Bravo test last year released 15 megatons, nearly 1,000 times more powerful than Hiroshima. And that was just the beginning.
Oppenheimer's face had grown pale. Are you suggesting that nuclear weapons could somehow damage time itself?
I am suggesting that we do not understand the full implications of what we have unleashed, Einstein replied. My equations describe how energy warps space-time, but they assume equilibrium conditions, gradual changes over cosmic timescales. What happens when we create sudden, massive disturbances? What happens when we punch holes in the continuum faster than it can heal itself?
This was not the Einstein of popular imagination, the gentle pacifist who regretted his role in creating atomic weapons.
This was Einstein the physicist, following his theories to their logical conclusions regardless of where they led. He had spent decades developing the mathematical framework that described gravity as curved space-time. Now he was discovering that this same framework might predict consequences no one had anticipated. His unified field theory took on new urgency in this context. If he could find the deeper pattern that connected all forces, perhaps he could also understand how those forces might be disrupted by human intervention. The equations that governed electromagnetic fields and gravitational fields might also govern the stability of space-time itself. But the mathematics proved intractable. Page after page of his notebooks showed false starts, promising approaches that led to contradictions, elegant solutions that collapsed under closer examination. The unified field theory remained tantalizingly out of reach. Like a melody he could almost but never quite remember. What troubled me most was watching Einstein grapple with the unintended consequences of his own greatest discovery. E equals mc squared had seemed like pure science when he first arrived at it in 1905. A simple statement about the equivalence of mass and energy. But that innocent-looking equation had made atomic weapons possible. The energy locked inside the atom, invisible for all of human history, could be released by anyone who understood the mathematics. I made one great mistake in my life, he confessed to me one February afternoon as snow fell outside his study windows. When I signed the letter to Roosevelt recommending that America develop atomic weapons, we were afraid the Germans would build them first, and we were probably right to be afraid. But I did not foresee what would follow. I thought we would build 1 or 2 bombs to end the war, and then return to peaceful research. Instead, we had built thousands of bombs, each more powerful than the last. The Soviet Union had matched our arsenal. Britain and France were developing their own nuclear capabilities. The weapons Einstein had helped make possible were spreading across the globe like a contagion, and there seemed to be no way to contain them. The discovery of nuclear chain reactions need not bring about the destruction of mankind, any more than did the discovery of matches he had written in 1946, trying to maintain his optimism. But by 1955, his optimism had given way to something darker. The matches had become flamethrowers, and humanity seemed determined to burn down its own house. In his unified field equations, Einstein was searching for more than scientific understanding. He was searching for hope that the universe possessed some deeper stability, some mechanism that would prevent us from destroying ourselves through our own cleverness. But the mathematics offered no such comfort. If anything, they suggested that the damage might be worse than anyone had imagined. Robert Oppenheimer carried himself like a man who had seen too much and understood even more. Where Einstein's concerns were largely theoretical, rooted in mathematical speculation about space-time and unified fields, Oppenheimer's knowledge was visceral,
Earned through years of translating theory into terrible reality. He had been there when the first atomic bomb exploded in the New Mexico desert. He had seen the flash that turned night to day, felt the heat on his face from 20 miles away, watched the mushroom cloud rise into the stratosphere like humanity's darkest prayer made manifest. I remember the line from the Hindu scripture, the Bhagavad Gita. He told me during one of our March conversations, his fingers tracing the worn leather cover of his personal copy. Vishnu is trying to persuade the prince that he should do his duty, and to impress him, takes on his multi-armed form and says, "Now I am become death, the destroyer of worlds." I suppose we all thought that, one way or another. The book never left his desk, a constant reminder of the moment when theoretical physics became applied destruction. He had studied Sanskrit at Harvard, drawn to the philosophical traditions of the East even as a young man. The Gita's exploration of duty and consequence had given him a framework for understanding his role in the Manhattan Project, but it offered little comfort for what followed. Unlike Einstein, who had remained largely isolated from weapons development, Oppenheimer had lived inside the machine that transformed atomic theory into atomic reality. He had recruited the scientists, managed the laboratories, solved the engineering problems that turned uranium and plutonium into city killers. He knew exactly how the bombs worked, because he had overseen their creation from beginning to end. "People think the hard part was the physics," he said, setting down his teacup with characteristic precision. "But the physics was settled by 1942. We knew that uranium-235 would sustain a chain reaction. We knew that plutonium could be bred in nuclear reactors. The real challenge was industrial. How do you separate isotopes on a massive scale? How do you machine plutonium when it's so toxic that microscopic particles can kill you? How do you design an implosion system that compresses fissionable material uniformly?" These were the questions that had consumed 3 years of his life and the efforts of over 100,000 people spread across secret facilities from Tennessee to Washington State. Los Alamos had been the final assembly point, the place where all the components came together into weapons that could end the war or end the world, depending on how they were used. "We had a betting pool before the Trinity test," Oppenheimer continued, his voice carrying the distant tone he used when revisiting those desert days. "Not whether the bomb would work, but how big the explosion would be. Edward Teller, always the optimist about destruction, bet it would ignite the atmosphere and incinerate all life on Earth. He was joking, mostly. But we had actually calculated the possibility. The odds were low, but they weren't zero. I found this revelation deeply disturbing. They had proceeded with the test despite knowing there was some possibility, however remote, of destroying all life on the planet." When I asked him about the decision-making process, Oppenheimer's answer revealed the peculiar logic that governed their work. "We were racing against Germany, remember? Every month we delayed gave Hitler's scientists more time to develop their own bomb. Intelligence suggested they were closer than they actually were. We couldn't afford to be cautious when the alternative might be Nazi nuclear weapons, so we calculated the risks and decided they were acceptable." But Germany had surrendered in May 1945, months before the bombs were ready. The original justification for the Manhattan Project had evaporated, yet the work continued. The bombs that were dropped on Japan in August were not products of military necessity, but of institutional momentum. Too much money had been spent, too many resources committed, too many careers invested in the project's success to simply stop. "Truman asked me once how many people the bombs had killed," Oppenheimer said, his hands folding and unfolding as he spoke. "I told him the numbers didn't matter, that he was the one who dropped the bombs, not me. I was wrong to say that. We all dropped those bombs. Every scientist who worked on the project, every engineer who solved a technical problem, every administrator who kept the facilities running, we are all responsible for what happened to Hiroshima and Nagasaki." The weight of this responsibility had grown heavier over the years, not lighter. In 1945, there had been a sense that the bombs had ended the war and saved lives by making an invasion of Japan unnecessary. By 1955, with thousands of nuclear weapons deployed around the world, that justification felt increasingly hollow. The hydrogen bomb represented an even more troubling evolution. Where atomic bombs released the energy that held atomic nuclei together, hydrogen bombs forced light nuclei to fuse, mimicking the process that powered the sun itself. The energy release was potentially unlimited. There was no theoretical upper bound on the size of a thermonuclear weapon. When Teller proposed the super in 1949, Oppenheimer recalled, "I opposed it not because I doubted it would work, but because I feared it would work too well." An atomic bomb can destroy a city. A hydrogen bomb can destroy a civilization. What military target requires such destructive power? His opposition had been both practical and moral. Practically, he argued that the enormous resources required to develop hydrogen bombs would be better spent on atomic weapons and delivery systems. Morally, he believed that some weapons were too terrible to build regardless of military utility. "I testified to the Atomic Energy Commission that the hydrogen bomb was not a weapon, but a weapon of genocide. It cannot be used tactically. It cannot be targeted precisely. It exists only to kill everyone in a region, combatants and civilians alike, soldiers and children, the guilty and the innocent." But his opposition had been overruled. The Soviet Union's first atomic bomb test in 1949 had terrified American policymakers into authorizing development of the superfin. When the Soviets tested their own hydrogen bomb in 1953, the arms race entered a new phase entirely. Oppenheimer's security clearance revocation in 1954 had been punishment for his opposition to hydrogen bomb development, though it was framed as concern about his past associations and his judgment. The real issue was his growing conviction that nuclear weapons represented a fundamental threat to human survival, a position that put him at odds with the very institutions he had helped to create. "They painted me as a security risk," he said with bitter amusement. "But the real risk I posed was to their certainty. I understood these weapons better than almost anyone, and I was saying they were too dangerous to use and too dangerous to build. That made me inconvenient." Einstein understood this isolation intimately. His own opposition to nuclear weapons had marginalized him within the scientific community, reduced his influence to moral statements that policymakers could safely ignore. Together, they represented the conscience of atomic physics, two men who understood better than anyone what their theories had made possible. "Albert worries about the fabric of space-time," Oppenheimer told me during one of our conversations. "I worry about the fabric of civilization. Both may be more fragile than we assumed." The Bhagavad Gita on his desk served as a daily reminder of the eternal questions their work had raised. What is duty when the consequences are so terrible? What is responsibility when the knowledge cannot be unknown? What is wisdom when the choices are all tragic? In the ancient text, Prince Arjuna faces a battle that will destroy his family and his world, regardless of the outcome. Krishna counsels him to act according to his nature and his duty, accepting that some consequences cannot be avoided. But Oppenheimer had begun to wonder whether their duty had been to refuse the terrible knowledge altogether, to leave some secrets locked in the heart of the atom where they belonged. Robert Oppenheimer died on the 18th of February, 1967, in Princeton, 12 years after Einstein had passed. I was with him in his final days, watching throat cancer consume the man who had once commanded the most destructive force in human history. His voice, which had once briefed presidents and testified before Congress, had been reduced to whispers, but his mind remained sharp until the end. 2 days before he died, he asked me to sit beside his hospital bed. His breathing was labored, his once elegant hands skeletal against the white sheets, but his eyes still held that peculiar intensity, the look of a man who had seen too much and understood even more. "David," he said, his voice barely audible, "you were there for the conversations with Albert. You heard what he feared about time itself." I nodded, remembering those afternoon tea sessions when Einstein had worried aloud about space-time fabric and the wounds we might be inflicting on reality's structure. "I want you to remember something," Oppenheimer continued, pausing to gather strength. "Albert was right about more than we realized. The damage goes deeper than cities destroyed or lives lost. We tore something fundamental, and it hasn't healed." He was referring to evidence that had accumulated over the years since Einstein's death, observations that supported the old man's fears about nuclear weapons affecting the very structure of space and time. Atomic clocks near former test sites showed minute but measurable irregularities. Radiation monitoring revealed patterns that shouldn't have existed if the effects were purely local and temporary. "Promise me," Oppenheimer whispered, "that you'll continue to watch, to measure, to understand. Someone has to bear witness to what we've done." I promised, and I have kept that promise for over 50 years since his death. The evidence has continued to mount. Modern atomic clocks, precise to billionths of a second, show consistent temporal anomalies in regions where nuclear weapons were tested. The Nevada test site, Bikini Atoll, the Semipalatinsk polygon in Kazakhstan, all display subtle but persistent distortions in time flow. The differences are tiny, measurable only with instruments
far more sensitive than anything available in Einstein's day. But they are real, and they are permanent. Satellite gravitational measurements reveal corresponding spatial distortions, regions where the geometry of space-time remains slightly curved, decades after the nuclear explosions that created them. It's as if the fabric of reality bears permanent scars from humanity's experiments with stellar-level energies. Einstein's unified field theory, which he never completed, might have predicted these effects. His notebooks from the 1950s show increasingly sophisticated attempts to model how massive energy releases would propagate through space-time. If he had lived another decade, if the mathematics had yielded to his persistence, he might have developed a complete theoretical framework for understanding the damage we were inflicting. But perhaps it's better that he didn't live to see the full confirmation of his fears. By the time I write this, 9 nations possess nuclear weapons. The global arsenal contains over 13,000 warheads, many hundreds of times more powerful than the bombs that destroyed Hiroshima and Nagasaki. The hydrogen bombs Einstein dreaded have grown from experimental devices to routine components of military arsenals. The Cuban Missile Crisis in 1962 brought the world within hours of nuclear war. The Able Archer 83 exercise in 1983 nearly triggered a Soviet first strike based on misunderstood intelligence. The Kargil conflict in 1999 saw nuclear-armed India and Pakistan exchange artillery fire across their border. Each crisis passed without nuclear exchange, but the accumulated stress on space-time has continued to grow. Modern physics has begun to recognize what Einstein intuited in his final years. Quantum field theory describes space-time as a dynamic medium, constantly fluctuating at the smallest scales. General relativity shows how massive energies warp the larger structure. Nuclear weapons, with their ability to convert matter directly into energy according to E equals mc squared, create disturbances that propagate through both quantum and relativistic domains. The effects are cumulative. Each nuclear explosion adds to the total damage, creating overlapping zones of temporal and spatial distortion.
Satellite monitoring now tracks these anomalies routinely, though the data remains classified by most governments.
The public focus remains on radiation fallout and political consequences, while the deeper structural damage to reality itself goes largely unrecognized. I sometimes wonder what Einstein and Oppenheimer would make of our current situation. The Soviet Union, which once seemed an existential threat to American civilization, collapsed in 1991. The Cold War, which drove much of nuclear weapons development, ended without the superpower confrontation both men feared. Yet the weapons remain, spread among more nations, maintained by military establishments that have forgotten the original context that created them. Climate change, which neither Einstein nor Oppenheimer anticipated, has become the dominant global threat. But nuclear weapons remain the only force humans have created that could end technological civilization within hours. The space-time distortions they create may prove to be permanent additions to Earth's physical structure, scars that will outlast the civilizations that created them. Young physicists today work with equations Einstein would recognize, applying general relativity to understand black holes, gravitational waves, and cosmic evolution. But few of them consider how nuclear weapons might fit into this framework. The connection between atomic bombs and cosmological physics remains largely unexplored, relegated to classified research programs that publish no results. Oppenheimer's fears about civilization's fragility have proven prescient as well. The institutions that develop nuclear weapons, the scientific laboratories and military establishments and political authorities, have proven remarkably durable. But the broader social fabric shows increasing strain. Democratic norms erode. International agreements crumble. The careful balance of power that prevented nuclear war during the Cold War has given way to more chaotic and unpredictable arrangements. Both men understood that nuclear weapons represented more than military technology. They were expressions of humanity's relationship with nature itself, demonstrations of our ability to unlock and manipulate the fundamental forces that govern reality. The question they wrestled with in their final years was whether we possess the wisdom to handle such power responsibly. The evidence suggests we do not. The space-time distortions continue to accumulate. The weapons continue to proliferate. The delivery systems grow more sophisticated and harder to defend against. Each year brings new technological capabilities and new opportunities for miscalculation or malice. Einstein's warning to Oppenheimer about destroying the fabric of time was not metaphorical. It was a physicist's assessment of what nuclear weapons might do to the structure of reality itself. That warning has been vindicated by decades of careful measurement, but it remains largely unheeded by the policymakers who control these weapons. I am 93 years old now.
one of the last people alive who witnessed those conversations between Einstein and Oppenheimer in the 1950s. My own research career has focused on the intersection between nuclear physics and general relativity, studying the space-time distortions that nuclear weapons create. The papers I've published hint at the larger implications, but the complete picture remains classified.
When I am gone, others will have to carry forward the understanding Einstein and Oppenheimer achieved through their collaboration. The atomic clocks will continue measuring temporal anomalies.
The satellites will continue mapping gravitational distortions. The evidence will continue accumulating that we have damaged something fundamental about the reality we inhabit. The fabric of time, as Einstein feared, bears permanent scars from our nuclear experiments.
Whether those scars will eventually heal, or whether we will continue tearing new ones until the damage becomes irreversible, depends on choices future generations will make with knowledge we help to create.
Einstein's final warning was not about nuclear war, though he feared that too. It was about the deeper responsibility that comes with understanding the forces that govern existence itself.
We have learned to split atoms and fuse nuclei, to convert matter into energy with perfect efficiency, to release in moments the power that stars accumulate over millions of years.
But we have not learned wisdom.
And until we do, the fabric of time will continue to bear the wounds of our cleverness. Permanent testimony to what happens when knowledge outpaces understanding, when power exceeds wisdom,
When the children of Einstein and Oppenheimer inherit weapons too terrible to use and too dangerous to abandon.